So the learning paradigms discussed above result in an adjustment of the weights of the connections between the units. So what are these connections between the units is what? This is the connection between the units. Okay, one neuron, the another neuron. So there is a connection, and the strengthening the axon or regulating the signal in the axon is highly mediated via giving variable values in the weight factor. Okay, so that's what the sentence says. So when we adjust the weights of the connection between the units, we can even work out according to the some modification rule. So perhaps the most influenced work in the connectionism's history is the contribution of the scientist called Hebb, where he presented a theory of behavior. See what the basic things what we are trying to, whenever we say the training the model, training the neuron network, okay, that everything is based upon a concept which is theory of behavior. Based upon the behavior, every parameters are fine tuned. Okay, so these are all the ancient theories, and when Herb in 1949, he presented a behavior, a theory of behavior. Okay, and this is based as much as possible on the physiology of the neuron system, okay, or the nervous system. Okay, so this Herb postulates some rules. The most important concept to emerge from Herb's work was his formal statement, what we normally say that Hebb's postulate of how learning could occur. Means, first of all, we have to understand the behavior, okay, and the behavior of the network. And first of all, we should know how the input, or the output of the network is influenced. What are the parameters is directly influencing the output. So, in all these things, we should take a history. Then we have to go for a learning process. So, how the learning could occur. So, we make the model to learn the data. So the learning was based on the modification of synaptic connections between neurons. This is nothing but when we talk about this is the connection between the units, this is the main issue here. So when we talk about learning, so we have to work on the modifications of synaptic connections between the neurons. So when an axon of a cell A is near enough to excite a cell B, and repeatedly or persistently takes place in a firing it, then some growth process or some metabolic change takes place in one or both cells. Now I am coming back. This is a biology as well as mathematics issue. I am coming back to the same concept. So whatever is that, I said, are you seeing the figure now?
Yes,
So we need a sufficient energy to trigger or to activate the neuron. Okay. So when a cell is fired, means when a cell is activated, okay, it will pass some information. This is one incident. But if a cell is continuously fired, okay, what happens? The signal is processed in the body, and the signal is processed output is transmitted in the axon. Okay, so continuously what is happening, this information is passed on and the information will come at the synaptic terminals. When the synaptic terminals are like this, what will happen? The same dendrites will come and get its own input. So synaptic terminals are ready with output and the dendrites are ready to receive this output as an input signal. What is happening? Next to this ending point, we have some plasma membrane or some medium where the energy or the output is introducing a chemical signals. Okay, it is releasing some chemical signals, and the chemical signal is potential enough to pass on the same information to the dendrites. That is how one unit of neuron is ready to give the same information. Then in the another neuron, the dendrite is ready to receive the information. So there is a constant metabolic changes in the connection point as long as the cell is ready or fired to process the signal. So everything should be set on in order to transfer the information from one neuron to the another neuron. You all agree with this?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
But I'm reading the same sentence again. So when an axon of a cell A is near enough to excite a cell B and repeatedly, because that has to go on continuously, then only the information can pass on, it can receive and it can react, okay? And persistently takes place in firing it, then whatever the new thing is happening is some new growth process. Probably, when a small kid, we can talk about growth process, or we can also talk about some metabolic change, anything. Okay, metabolic change takes place in one or both cells. Either one neuron involves, or both the neurons are involved. Such that, so what is the condition here? That A's efficiency as one of the cell firing B is increased. So that efficiency of A should be higher enough to fire the B in a repeated manner or in a persistent manner. So these principles underlying this statement have become known as Hebbian learning. What is normally the Hebbian learning? Virtually, most of the neural network learning techniques can be considered as a variant of the Hebbian rule learning, because this is the basic. It has to persistently give an input and it has to be in a firing state. So this is the Hebbian learning, and we every changes, advancement in the Hebbian learning is implemented. That's what they say, the variant of this Hebbian learning. So the basic idea is that if two neurons are active simultaneously, their interconnection must be strengthened. Why? Why it has to be strengthened? Because there's a loss of energy when it is activating, when it is performing. There's a loss of energy, and the loss of energy should be compensated by additional input. So every time the axon may go weaker, so you should strengthen the connecting unit. You understand what I'm trying to convey?
Yes, ma'am.
Okay, so the basic idea is that if two neurons are active simultaneously, their interconnection must be strengthened. If we consider a single layer network, one of the interconnected neurons will be an input and the one will be an output. So, what is this one single unit? This is the single unit. One layer input, the other layer output. And neurons will be one of the interconnected neurons will be an input unit and one as an output unit. If the data are represented in a bipolar form, it is easy to express the desired output as. What is a bipolar form? What is a bipolar form? Any idea? Okay, when you are giving a signal, I don't know, but anyway, let me draw. We can wait. Okay. So what is this called? Any idea?
Now wave.
Okay, it's a sine wave, right? And if I do like this, it is a cos wave, right? Okay. So if I say like this, it is a pulse. Okay. And if I do like this, you have one polarity and the other polarity. So it's a bipolar signal, right? So normally we can put bipolar because it has a positive direction as well as a negative direction. Okay. So now, okay. So if the data are represented in a bipolar form, it is easy to express the desired weight. So first we are going to write the equation for only how we are going to change the existing weight with the old weight. Okay. Now the problem, let me read this. We have a network where we have an input given to 1 to n inputs. Okay, you now imagine the figure 1. We have an input and we have and the dimension of the input is n. Okay, and with that input, we have some operation in the body that is in the node, and we are giving the output as a desired output. Okay, so based upon our equation, normally what we'll have, we have that n number of sorry xi, that is xi means I goes to 1 to n, and accordingly we have a output xio. And with this parameter, and we are also taking the old weight, and by summing these two we are going to take a new weight. Okay, this is coined by this scientist called Hebdo. So in a Hebbian learning process, every what is that? When the two nodes are constantly fired, their connection should be strengthened. And so we have to change the weight in order to strengthen the connections, and in such a way that we consider the old weight plus the desired output and the components for individual x. Okay. So all these things put together, we are going to find a new weight. And what we are going to do is, when we are going to find out this new, then what happens is this Hebbian learning continuously strengthening its weight without bound. What here? There is one drawback here. Any new weight can be from the old weight from this contribution. So there is no limit for reaching the new. It can be anything. So this is naturally acceptable to some range. It is not acceptable in all ranges because this is only increasing order. There is no saturation level. So even though the Hebbian learning is easy, just to know from their pulse and to strengthen, but it cannot be taken in all cases. Okay, so what people do is, keeping this Hebbian learning as a base, people started using a little modified version of the Hebbian learning that is called the perceptron learning rule. What is this perceptron learning rule? This is also nothing, but it's not very difficult. Little bit screening component is added. What is that? The perceptron is a single layer neural network whose weights and biases could be trained to produce a correct target vector when presented with a corresponding input vector. So now let us see what we are going to have. I will read this once and then I'll come back. The training technique is used is called the perceptron learning. Here in Hebbian learning, we are directly modifying the weight. But here in the perceptron learning, we are trying to give a training technique. What is that? The perceptrons are especially suited for simple problems in pattern classification. What is this? Suppose we have a set of learning samples consisting in an input vector x, and accordingly we have an output, desired output, that is d of k. So we have a set of input vectors, and for that vectors we are getting a desired output, that is d of k. And for a classification task, This d of k is usually plus 1 or minus 1. Okay, so what happens? It is a bipolar function. So this will have one amplitude in the positive direction and amplitude 1 in the negative direction. So the perceptron learning rule is very simple and can be stated as how they are going to work. Start with the random weight for the connections. So here what they are saying, you go with any random connections of the weight and select an input vector x from the set of training samples. So you can choose any input vector. But if the output yk is not equal to the desired k, then the perceptron gives an incorrect response. This is natural. And what we have to do? You have to modify all connections, all weight parameters according to a condition that's a del, a small change in the weight wi, that is del wi is equal to, there is a factor. What is this factor? This is eta multiplied by dk minus yk into xi. What is this dk? This is the desired output. What is your yk? Whatever the output the model gives. And you take a difference and feed it to the xi, but it is scaled by a new parameter called the learning rate. So there is a level of learning rate in every xi. So accordingly, we derive a factor and that factor we change this as a del wi. This del wi we will add it to the, what is that? Terminal. So you go back to the x step 2 means input vector xi, you take this and xi plus del wi you give it, then you keep on doing this. But here note that the procedure is very similar to Hessian rule, but the only difference is that when the network responds correctly, no connection weights are modified. You remember in the previous pages we say that when a neuron is set fire continuously and the response is not disturbed by the changes in the weight. The last class we read it. So the advantage is that once you start fine tuning the weight between the two connecting units, then and when the network is responding properly, then there is no need for any adjustment in the weight. Okay, so here the delta wi is a parameter that describes how you can increase the weight and add it to the weight factor. Okay, this is scaling, this is a scaling parameter, and every increment you can do this according to your output, and they take the difference and you can scale it by the learning rate. Okay, so these are all the things, the parameters. You don't worry about it. You learn the logics, but it is not urgent because we are not going to do any program on this and execute this as a tutorial. You understand what I'm trying to say? So today we learned two things. One is the Hebs learning process. The other one is the perceptron learning rule. In the Hebs learning process, there is a strengthening of the connective units. So with the help of taking a multiplication of xi in O and adding the weight. But here there is a drawback because every O vector you can go with the increment. There is no limit for this. So in order to make sure that there is a scaling and the introduction or the change in the weight should be limited for the purpose of continuous firing the signal. So they introduced the perceptron learning rule. So the perceptron learning rule is nothing but a change in the weight factor delta wi, which is derived as eta into dk minus yk into xi. So this we will be using it in the do loop as long as the delta wi becomes consistent and you know the node is really set on a stable state and it is passing or keep on processing the input signals continuously, then there is no need for any change in the weight. You understand? Students,
Yes, ma'am.
Yes, ma'am.
is it okay? You guys are following?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Is it okay, or you are simply saying okay? Okay. So I will leave this today, and we can do this in the next class. Maybe this is the logic, so you have to read. So then only we can pass on to the next thing. So I will leave this to you, and we will see in the next class. Okay. So now today you learned two things, learning rules. One is the Hebb's learning rule, the other one is the Kapsapan learning rule. Please give a read, and immediately after I finish this unit, finish this article, I will keep internal one. Okay.
Okay, ma'am.
Okay, ma. Okay, ma. Thank you, ma.
Thank you.
Thank you, ma'am.
Okay, ma.